Hey, quite a while ago, probably 160-ish years ago, something like that, um, we would have a problem coming up with the structure of a molecule. So this guy named Dr. Lewis came up with a way to put atoms together to simulate a structure. Now that's what the dry lab is this week. You're going to be practicing this. Be nice now. Um, so what he thought was, and it's still true today, is that there are two kinds of electrons. Ones that are extremely stable and ones that are not. Okay, so we're going to call the super stable ones core electrons. Now, if something is super stable, it doesn't want to change. It wants to stay super stable. So, those electrons don't do anything. Now, electrons that are not stable are called valence electrons. And those electrons occupy the outermost orbital. Because they're not stable, they want to become more stable. And they do that by combining with other electrons. We've got valence electrons, core electrons. We're not going to talk much about the core electrons. We're going to talk a lot about the valence electrons. All the chemistry is a valence electron, except for okay, so what Lewis did, he put together a chart of some of the most common atoms and their valence electrons. Now, the important part on this is whenever we have an unstable electron, an unstable valence electron, and it's unstable, the main way it becomes more stable is to pair up with someone, meaning another valence electron in another atom. I'm saying single electron because when these pair up, we've got to pair up from pair. Hence the word pair up is used a lot in chemistry. The path valence electron unstable. The path to stableness is pairing up with another electron. And usually it's a valence electron. So valence electrons want to pair up with one another for stability reasons. So here's carbon, hydrogen, oxygen, nitrogen. Notice there are no noble gases there. That's something a noble gas electron all of them are already paired up. So all of them are on the scale. So you didn't include any noble gas detectors. Hydrogen is the most prolific atom in the universe, not just Earth, but the universe. So definitely include that. Carbon. Carbon is very common on Earth, particularly when we talk about life. Think about without chemistry here. Light chemistry, biochemistry, with a lot of nitrogen. Some fluoride. Okay, so notice there's more up there. Now, if you remember from the periodic table discussion, the atoms that are in a column with one another have similar chemical characteristics. The reason for that is the valence electrons are the same. So in a periodic table, in a column, they all have the same properties. Group one, they form +1 ion. All of them. That's because of the valence setup. Group two, they form a +2 ion. All of them. So calcium, strontium, barium, and etc. All of them. And that's because if you look at their valence setup, it's the same. Core electrons, no. It doesn't matter about core electrons because they don't do anything. The valence electrons. So if we look at nitrogen, what is underneath nitrogen? Sulfur is underneath oxygen. Oh, okay. So notice the valence electrons on those two. Three singletons in one pair. Three singletons in one pair. Now notice that the pair is in a different location in nitrogen. You're going to see when you start configuring stuff, you can move that stuff around. As long as you keep the pairs together, singleton, single. So we would put, they don't have P if there's nothing under nitrogen. You're going to have one pair and three singletons. Oxygen, what does that mean oxygen? Sulfur. Notice sulfur, oxygen, same valence. So we don't need sulfur up there because you now oxygen. Look at fluoride. What's underneath fluoride? Fluorine, the valence electrons are the same. Three pairs, one single. Now, when we're constructing atom to atom, we're making a bonding pair of electrons. Bonding pairs have two electrons. The orbital doesn't have enough room for any more than that. So singletons will hook up with another singleton. And there's more room in that orbital. If you have three singletons, that means it's going to have three bonds. Now, those three bonds can be a triple bond, that means three pairs. It can be a double and a single, or three singles, as long as they add up to three bonds. Okay? How many bonds in carbon? Four. Four, because four singletons, yeah. Right? So when you look at the singleton, that's how many that atom wants to create bond-wise. For singles, four bonds. For carbon, you have a combination of a triplet and a single, or single, two double bonds, one that adds up to four. Now, in my organic class, I don't teach anything about fluorine because it's not in the body. You guys are going to either 1A, 2A, or 3A. So we're going to introduce some fluorine type atoms in this project. So we're going to include fluorine when we talk about stuff. Okay. None of you have asked me, do I have to memorize that? Okay. Yes, you do. But there are only four you have to memorize. That whole five if you count from the side. Hydrogen. How many bonds hydrogen do you want? One. One. Okay. Carbon, the next area wants four bonds, oxygen two. So it kind of goes in order. Start at carbon. What's next to carbon? Nitrogen. What's next to nitrogen? Oxygen. What's next to oxygen? Four. And keep adding one valence electron each time. So you memorize carbon, which has four. And look at the periodic table, the next one over has an extra one. Five and four. But two of them are paired up. There's three singletons of nitrogen. One more. We add another electron. Six now. Two singletons pairs. And then jump over to chlorine. Add another one again. Got three pairs, one singleton. You know, carbon, hydrogen doesn't fit in that line, but hydrogen has one bond. To learn these two, and just with the periodic table, just go across. As you go across, keep adding electron at a time. So it's not too bad as far as memory. Okay. Well, no, not over. Maybe about.
All the doubles are satisfied, right? There's only the single dots that want to be paired up.
Exactly. Yeah, pairs are already stable. There's no reason to get more parallel.
Yeah.
Singletons are, they definitely want to get parallel. So if we put here's carbon, and this is the, we haven't talked about atomic structure yet. This is the Bohr atom here. Bohr atom is based on the planetary concept, like we have in the solar system. Yeah, inner electrons revolving around the nucleus, and then you have other orbitals revolving around the nucleus. That model is no longer in use. We use a quantum mechanical model now for the last 120 years or so. But for this kind of stuff, it's much simpler than the quantum mechanical model. Okay, so if you look at this orbital diagram for carbon, we've got two orbitals. The outermost one is the valence orbital. The innermost one is the core. Now, carbon has 6 electrons, so 4 valence, 2 core. 4 plus 2 is 6. Now, uranium has 92 electrons, so it's got a whole bunch of orbitals. Now, say we wanted to hook up carbon with something else. Let's say we wanted to hook it up with nitrogen. We're going to have a carbon nitrogen molecule. Let's look at the way the valence electrons are going to fit into those. Now we know carbon has 4 singletons. Nitrogen has three singletons, and a pair. Now remember, I could move the pair around for convenience. I'm going to put it away from the carbons. Okay. Now, nitrogen wants to make three bonds because it's got three singletons. So when carbon gets close to nitrogen, these start hooking up. So we have bond, bond, bond. Now look at the nitrogen. Does nitrogen have any singletons left over? Carbon does. So because carbon still has a singleton left over, this is not a stable molecule because it's got an unbonded singleton. So this guy is going to be in search of something with a singleton electron, like hydrogen, for example. So now carbon has four bonds. Nitrogen has three bonds. No singleton electrons left over. So this is hydrocyanic acid. Extremely funny. And very stable. Why is it stable? All the singletons are used up. Sometimes you have to use singletons in cases where we have a double or triple bond. And then lastly, what we do is put a solid line where there's a bond. So that's the end product of the Lewis dot structure. So we've got some rules. Okay, so these 6 steps is what we just did. And steps 4 and 5 have to be followed if you want a legal Lewis structure. Verify each atom has a perfect number of bonds. Carbons are 4, nitrogen 2, oxygen 2, hydrogen 1, and hydrogen 1. Step number 1. Map your carbon bond where the singletons are paired up. Also evaluate each step so that each atom has 8 electrons, called the octet. That's a hydrogen. Now, that octet is looking for are a combination of shared electrons all together on the next atom over or atom state. And everything needs 8 except for hydrogen. And when you get into 1A, you'll learn there are 12 or more than 8. For here, it's 8. Okay? I mean, we're doing more wild than that. Okay, and this is on Canvas, by the way. As well as the worksheets. And I'm going to go through it here. Now, on your lab today and tomorrow, it's a 2-part lab. We're going to be doing just part 1, which is, guess what? Draw the Lewis structure. Now, this is one of the essential skills for Chem 1A, 2A, and 3A. You absolutely need to know this going in there. Because they're going to go over this in a much more complicated way, number 1. Number 2, we're going to zoom through it. Especially 1A. Zoom through it. Okay, so let's look at some more examples. Let's look at ethylene. C2H4. Okay. Step number one is take the most complicated of the atoms that I went over. In other words, the most singletons, those go in the middle. Okay, when you look at carbon, hydrogen has one singleton, carbon's got 4 singletons, so the carbon goes in the middle. Let's make them bigger. Okay, that's step number one. Put the most complicated one in the middle. And we're not done yet. We need to deal with the hydrogens. Now there are 4 of them, so I'm going to put them kind of around the 2 carbons. It does not matter where. Let's put one here, here. Okay, so that's step one. Lay out. You've not done any bonding yet. You just lay it out. So now we're going to start connecting electrons together. Bonding the unstable electrons. So here, here, here. Let's look at those. Okay, everything has got at least one bond. So you go through in this step, hook everything up, singleton to singleton. Now, ask yourself, are there any singletons that are non-bonded? Okay. You can't leave them that way, because this is very unstable. Like these are called free radicals. Have anyone heard of free radicals? They are not nice. They are so bad that they will bond in the closest thing to get rid of a singleton. Free radicals are frequently created during a nuclear accident. Another reason why it's not good to have a nuclear accident. Who in here has seen the series Chernobyl? Anyone? Wasn't that nicely done? And most of the science, I was picking in science, it's right on. And that's the reason why we don't make those kind of reactors. If you get a chance, it's a long series. What is it, like an hour and a half? There are 4 episodes. Yeah. The hour and a half a piece for at least an hour. So it's a chunk of time. So do that on your break or after classes over. But it's really worth your time. It's fascinating. Not only for the science, also for the politics. Yeah.
It's called.
It's called Chernobyl. It's just on YouTube, and it'll that and another 2,000. Okay, so we do have 2 unpaired singletons. Got to pair them up. Okay, no more singletons. Now, what we formed is a double bonded carbon. So before this, let's check to make sure this is legal. My cough is almost gone. Okay, so remember the steps. Carbon needs 4 bonds. 1, 2, 3, 4. That's good for this one. Check this one here. We're counting shared bonds now. 1, 2, 3, 4. So carbon's good. Hydrogen needs 1, 1, 1, 1, 1. So that part's legal. Let's look at the octet. count all electrons each atom's got, okay? And we count the shared ones as well. So we got 2, 4, 6, 8. 2, 4, 6, 8. So that's a legal structure. For legal structure. Now, the next thing we do is you make it pretty by drawing lines for each bond. So ones for the dots. Really good. If this is not legal, you can find what's wrong. Then just do another one. Out of the electron dot. Okay, so we just need to practice this like a lot. Okay, is everyone clear on this? Yep. Now, if you read your book how to do this, they have like 15 steps. And if you count valence electrons and you start subtracting off the top of the valence electrons, you hook everything up with one bond. How many electrons does that use up out of the total? And then you got to, it's like extra steps. So I usually go to look at your book. Okay, so let's do some more examples. Notice these are neutral. Let's do an ion now. Let's do a neutral one. Another one is an example. Then we'll do that. Okay. Let's see. Okay, this is formic acid. This is what red ants have when they bite you. They get formic acid into the wound they create. Okay, so we've got 2 oxygens, 2 hydrogens, 1 carbon. Okay, so let's do start putting dots down here. Okay, we've got carbon in the middle. We have 2 oxygens now.
Why it's not just H2, CO2? Would that still be the same?
Yeah, they're equivalent. The reason I did it this way is formic acid can help against it. And acid will learn to give up hydrogen ion. So this is the one that comes off, not this one. So it's organic acid, you need to start with COOH, and that's your force. Another good question. These are equivalent. How many oxygens? 2. How many hydrogens? 2. How many carbon? 1. They're equivalent. But I wrote it as an organic chemistry wrote it. Organic, Huh?
This one's neutral as well?
And so that means there's no charged particle around. Okay, so we put the carbon down. We have 2 oxygens. And again, we can stick them anywhere we want. So let's put one on either side of the carbon. And we have 2 hydrogens. Let's just now there's a funny story about formic acid. The sun. The sun was very mischievous. He's the type that used to burn ants, the magnifying glass, that kind of kid. And he decided to boil fire Ray. See what came up with. Somehow got the answer, boiling water. And then his dad came out, saw what he was doing, and he said, stop the movie, all the data. Then the father, being a chemist, he decided to analyze the lymphocyte. Formic acid. And in Latin, they would know Latin. And some of you know Spanish. What did he say? Ant in Spanish. If you look up the Latin version instead of the Spanish version, it's called forma. That's how it's got its common name. And anyway. Okay, okay, next up is connect the dots. And make sure everything has got at least one connection. Singleton to singleton. Okay, now. If there are any singletons whatsoever. One hiding there. These two singletons. These two singletons. Unpaired. You need to pair those guys up. I'm going to connect that hydrogen over here to this other singleton. Okay, so we've got a pair of singletons on each of the carbon and oxygen over here. We need to pair those up and leave them unpaired. Now, I made a mistake, didn't I? The one on the right, correct, one on the left, no. What do you want? Here. That's the one. Good. Everyone see that? I only one pair of them. Okay, so let's redo that part of it here. Okay, now let's start connecting dots again. Okay, so we have one here. Now, this is why it's nice to work with a pencil. Trace. One. Have. Okay, so what's going on? That's not bonded. What are we going to do? That's right. So let's rethink the bonding arrangements here. Okay, the carbon right now has 3 singletons. The oxygen has 2 singletons. Anyone have any idea how to get this up legally? You keep assuming this hydrogen and oxygen go bond together. Well, let's move this one here. But looks like the carbon. Instead. We're going to move that hydrogen there over near the okay, so let's look at this again now. Okay, so this is going to be bonded. Now we've got carbon with two singleton and oxygen with two singleton. But for sure we have to bond at least one. That still leaves a singleton unbonded. So what we're going to do is we're going to do a double bond to carbon. Okay, so we've got now I'm going to draw it and I'm going to redraw it. Okay, and the reason why I have to redraw it is you'll see in a second here. Okay, so if I just arbitrarily went this guy and this guy, that's kind of a awkward looking. So what I'm going to do is I'm going to unbond it. I'm going to move some electrons around. And move, remember I said you can move the pairs around as long as you keep them as pairs. So I'm going to move this pair here up to the other side. Now when I draw the two bonds, it isn't all confused. Okay, so it's legal. Are there any unfair symbols? No. Oxygen needs two bonds. One, two. One, two. So oxygen are okay. Carbon needs four bonds. One, two, three, four. Carbon needs four. Okay. Everything except hydrogen needs an octet. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Hydrogen needs two. So we've got 2 and 2. So it's still a legal structure. And this is what formic acid looks like. So we've got carbon in the middle. We've got a double bonded O. We've got an H. Single bonded O. Okay, so that's what formic acid looks like. Always include the unbonded pair. This hydrogen here is the one that we can see. Now, those troubleshooting deals we just went through is what you're going to be faced with when you're drawing these. You start testing it, doesn't work. So we got to kind of erase it and start over again. And you keep trying it so it meets the two requirements. Number of bonds, octets. Okay, if those aren't met, it's not a legal structure. That's why a big eraser and a pencil work really well. Okay, so that's neutral. That's neutral. Let's look at an ion. Okay, screen. let's get a close of an eye. Oh, no. On your dry lab today and tomorrow, on the first page, they want you to do carbon monoxide. I want you to change that to carbon dioxide. First page of your, I think it's the first page. The reason for that is carbon monoxide is weird. And it's in the beginning of your worksheets. It's crazy to have that in the beginning. So now it's not in the beginning. Well, let's look at the hydroxide ion. Very common ion, used a lot in toxic materials like lime and sodium hydroxide, calcium hydroxide, and a lot of chemicals that have hydroxide in them. Okay, so we're going to go through similar steps with an ion. But ions, as you know, have either an extra electron or two, or they're missing an electron. So in this case, we have an extra electron. That's what makes it a charge of -1. So do the oxygen. Now I'm going to put square brackets around it, signifying it's an electron. Now the question is, where do you put the extra electron? Well, as before, the first step was connect up singletons. So hydroxide have one bond. Next step is, are there any singletons unbonded? Do something. But we have an extra electron. How many electrons do we have extra? One. Okay, so this one extra electron now is going to go there. So now there are no unpaired singletons. So redraw it. Now the only difference between a three-dimensional ion, how to deal with the extra electron or the extra deficit electron. So here, the things are not paired up, very unstable. So by taking this extra electron in there, you satisfy that instability being a singleton electron in the bond. That is a positive ion, that ion, you would take an electron away. And this is where it gets tricky with carbon monoxide. Not an ion, and you're stuck pairing up some unbonded copy. Okay, so same steps. Go through with the complicated one in the middle. Surround it with simple ones that only have one bond. We make one bond, start with, there we go, and then check for singletons that are not paired up. We have one here. We have an extra electron. Now, in case the cation, a positive ion, we're going to take an electron away. You can see the way that works. And that's the way 1A teachers, 2A, and 3A teachers teach it too. And I think this is much. That's what I'm telling you. You use either one. Also, if you go online and YouTube, I mean, there are 3 sites on YouTube that are really good tutorials. The Khan Academy, you can get tutorials on a whole bunch of stuff. A bunch of stuff. Another one is the Organic Chemistry Tutor, and they tutor in all kinds of chemistry, not just organic. They started off with organic chemistry, then they branched off a lot. They did physics, they did biology, they did biochemistry. And then the last one. Sorry about that. And then the last one is a guy named Tyler DeWitt. Those 3 YouTube tutorials are really good. And there's a lot of them. You just have to be careful. The way people explain stuff, if it's different the way I explain it, you may get confused. So stick with the one where it's consistent with the way I present stuff. Okay. So what we're going to do is let's do a couple more examples. Let me see. Um, what is your okay, this is the ammonium ion, NH4. And as you can see, it's a positive cation. So let's draw the nitrogen. We need 4 hydrogens. All right. Operate. I guess I'll do that. Okay. Now, this is what's kind of weird with cation. I don't think any electron out there. This hydrogen appears unbonded. Fix that. Oh, there's no room down here. The way we're gonna do it. I'm gonna take out one of the electrons from the nitrogen. What I've just done is I created a singleton in the nitrogen that can bond with the hydrogen. Now nitrogen has no tip. Hydrogen has two. No singleton unpaired. That's when we get up. Now I just I just created the singleton for hydrogen. So
With the, just with the ions, we can take the element.
you either add or take away.
Okay, okay.
The ion.
How about the? When.
Yeah, add anything or take anything away. Ions, if it's plus, you take away. It's minus, we add. The question is, which are you gonna put? Yeah. Okay, and ions will be your trickiest problem in this guide. And on the very last page of your dry lab are two ions you have to do. One is this one here, and there's another one. I forgot which one it is. An anion. Okay.
Final product of that, you just take that electron out and you don't have to draw it anywhere. You just don't know it.
What humanity to do. This is one of those things like bouncing equations. You'll have an aha moment. Oh, but that doesn't happen like you do. So I have extra worksheets in Canvas. Okay. Here's the one with the steps. So in lab today, tomorrow, have this on your phone. Hold up. Okay. This is the one we just went over a little while ago. So anyway, these worksheets all are under Unit 2. That, you know, fine for the rest of them. Well, you don't cable further down. I don't know what's in it. Yeah, that or it needs a new cable or it came loose inside. But anyway. Doesn't matter, because we're done today. Okay, so are there any questions about, flow structures? We've had this before. We're going to go home and do it. And do like every other one or the third one and get it down pretty good. You can leave. Whatever you want to do. It's fine. But yeah.
I don't see any of the structures in the lab. It just says it's like, you know, something 12.
It's under molecule.
We're doing have 12. That's fine.
Yeah.
Yes, and the first step on my 12 is guess what? Create the little structure.
So we don't have to do the next.
Correct, what you want to.
Are you gonna go over that stuff tomorrow? Or we just don't want to do it?
Margaret and short down.
Okay.
Yeah, I was looking at it.
So the lab is in two parts. We're only doing part one. Part one is do the little structure.
But it's basically it's like.
Well, that's why next week, all this.
So it's for. Yeah.
I don't know. Oh, yeah. So, yeah, I know.
It's very interesting. We just don't,
I would know.
you know, I've heard you were doing it. It's the word. I mean, you start throwing it, like, this is what you want to talk to, right?
Yeah.
You will,
Yeah. I like extra credit of the problem. Oh, it was.
Yeah. No, wait. Right?
Yeah.
Yeah. I know. I know. I was actually thinking. Signing up. Like a volunteer in my class. But like it's, I was like.
Okay, yeah, I don't know, I think I have a lot that I need to get done. So it'd be helpful to have.
Shut this.
Yeah, to see.
It's the dry lap, right?
Yeah.
Really?